Welcome to the NASA High Power Rocketry video series. In this video, we'll discuss the basics of high power rocketry. What makes a rocket high power? Most of us are familiar with the small model rockets that are popular with children. High power rockets are similar in theory, but are larger and more complex, and use more powerful motors and more robust materials. They often use electronics to deploy parachutes and track the rocket's location. For these reasons, high-power rockets are more hazardous to build and fly. A high-power rocket is defined as a rocket that uses a motor with more than 160 Newton-seconds of total impulse. The total impulse is the total amount of energy in the rocket motor. Mathematically, it is the thrust of the motor integrated over time. These motors are H motors or larger. We'll go over what H means in the propulsion video, which is number 4 in the series. High-power rockets also use a cluster of motors that together exceed 320 Newton-seconds. They use a motor with more than 80 newtons average thrust. They use a motor with more than 125 grams of propellant, or they weigh more than 1,500 grams, including the weight of the motor. High-power rocketry is regulated by several federal agencies. The agency that regulates the airspace through which high-power rockets fly is the Federal Aviation Administration, or FAA. The FAA regulates all types of aviation, including airplanes and helicopters, gliders, parachutes, balloons, and unmanned rockets that we build. Any FAA-required paperwork for high-power rocket launches is usually handled by the local section of the National Association of Rocketry, or the Tripoli Rocketry Association. Most basic HPR flights follow one of 2 flight profiles. The first flight profile is referred to as either single deploy or apogee deployment, or pop at the top. This involves using an ejection charge to deploy a parachute at apogee, or the highest point during the flight just before the rocket arcs over and starts descending. The parachute then brings the rocket down for a safe landing. Apogee is the safest point for deploying the parachute because the rocket is traveling at the lowest airspeed. The apogee deployment event is usually controlled by an ejection charge built into the rocket motor. The single deploy method is what is commonly used in low-power rocketry. This is the most simple flight profile, but it has some drawbacks. First, if the apogee of the flight is high enough, or if the winds are strong enough, the rocket may drift off the launch field. Second, the timing of the ejection charge in the motor may not coincide with apogee. In this case, the rocket may be traveling too fast, and the ejection event may damage the rocket due to the forces exerted by the parachute. A flyer can use an altimeter that senses the change in air pressure to determine apogee and avoid the problem. We'll discuss recovery techniques in the recovery video, which is number 5 in the series. The second flight profile, called dual deployment, solves the problems associated with single deployment. In a dual deployment flight, the rocket travels to apogee, where an electronic barometric pressure sensing altimeter deploys a drogue parachute. This small parachute is sized so that the rocket will fall at a velocity high enough to prevent excessive drift, generally between 70 and 100 feet per second. Then, at a much lower altitude, generally between 300 and 700 feet, an electronic altimeter deploys a larger main parachute that slows the rocket down to a safe landing speed. Dual deployment solves the drift issues found in single deployment flight, but it comes with added complication of flying electronic altimeters. Most HPR flights that use smaller motors or fly to lower altitudes use single deployment. HPR flights with the larger motors or that fly to higher altitudes use dual deployment. For level 1 or 2 HPR certification, you can use either method. In order for your flights to be safe and reliable, the rocket must be stable. Stability is determined by a stability margin and a rail exit velocity. To determine the stability margin and the rail exit velocity, we need to understand some important parameters. Center of pressure, or CP, is the point on the rocket where the aerodynamic forces are balanced. There are many ways to calculate the CP, and the most common method in HPR is the use of the Barrelman equations. There are several sources online that show how to use the Barrelman equations, and your local HPR mentor should be able to explain a simplified method to use these equations. The biggest factors in the calculation of CP are the length of the rocket and the size, shape, and location of the fins. The purpose of having fins on a rocket is to bring the CP further back on the rocket. The next parameter is the center of gravity, or CG. CG is the point on the rocket where the mass of the rocket is balanced. Simply put, you should be able to hold the rocket at the CG without it tipping on one side or the other. One should always verify where the CG is on the rocket by balancing the rocket once the motor, recovery system, and full electronics packages are installed. One rule of thumb for stability in HPR is that the CG must be at least one body diameter, or one caliber, in front of the CP. This is the stability margin. Mathematically, the stability margin is the distance between the CG and CP divided by the airframe diameter. So if you are flying a rocket with a maximum diameter of 4 inches, your CG needs to be at least 4 inches in front of your CP, giving 1 caliber of stability, or a stability margin of 1. If your CG was 8 inches in front of your CP, you would have 2 calibers of stability, or a stability margin of 2. Most flyers recommend stability margins of 2 or higher. Another important factor for stable flights is the speed at which the rocket leaves the launch rail. This is the rail exit velocity. The launch rail keeps the rocket in a vertical configuration while the rocket is accelerating to a speed at which the fins cause the CP to be driven back behind the CG and keep the rocket stable. This exact speed is hard to quantify and varies based on rocket size, mass, and fin shape. A rule of thumb is that 50 feet per second is a speed at which the rocket is stable without the help of the launch rail. It's important to note that rockets connect to the launch rail with at least 2 rail buttons, one near the rear of the rocket and one further up the airframe, usually near the CG. Once the forward rail button has left the launch rail, the rocket could rotate if it has not reached a safe rail exit velocity. It's important that the safe rail exit velocity be reached before the forward rail button leaves the launch rail. Rail exit velocity can be increased by using a motor with higher initial thrust or by using a longer launch rail. Now let's briefly talk about how a very general high-power rocket is constructed. The basic part of the rocket is the airframe. This is the long, cylindrical part that gives the rocket its shape. At the top of the rocket is the nose cone. Nose cones can be conical or they can be a more complicated shape. Nose cones can be empty or they can house electronics. In the center of the airframe is the avionics bay, a compartment that stores things such as batteries, sensors, or scientific payloads and fits inside the diameter of the airframe. The avionics bay also houses the electronics used for recovery. At either end, bulkheads seal the avionics bay by tightening threaded rods with washers and nuts. On the outside of the bulkheads, U-bolts or I-bolts are used to anchor the recovery harnesses. At the bottom of the rocket, there is a subsystem called a motor mount, which is a motor tube and motor retainer to hold the motor in place, and a set of centering rings that keep the motor mount concentric with the airframe. The component that really makes a rocket look like a rocket is the fin set. Fins can be mounted directly to the surface of the airframe, but are generally mounted through the airframe and against the motor tube. This is called through-the-wall fin mounting and is much stronger than surface mounting. Some rockets may have additional fiberglass or carbon fiber reinforcement over the fins and airframe to increase the rigidity and lower the likelihood of failure due to increased aerodynamic forces. Long recovery harnesses keep the rocket sections tethered together after the recovery separation events. The ends of the harnesses are anchored to the airframe sections with hardware. Rocketry can be used to demonstrate many different real-world aspects of physics and classical mechanics. Motion is most commonly described in direction, distance, velocity, and acceleration. The relationships between these things make up most physics classes and can be seen and measured in the flight of your rocket. We discussed earlier the importance of attaining a safe exit rail velocity. The exit rail velocity of your rocket is something you should know before you attempt to launch it. You can use a rocket simulator to estimate this velocity, but you can also use standard high school physics equations to figure it out also. We'll demonstrate how to determine the exit rail velocity of a sample rocket by taking just a few measurements and then working through some common equations. First of all, we will need to keep our units in mind. For simplicity's sake, most of our calculations will be using metric units, but we will need to do some conversions between imperial and metric due to the standards of the hobby. For instance, we will need to convert our 8-foot launch rail into meters and our minimum exit rail velocity into meters per second from our known value of 50 feet per second. Let's begin with our known values and these conversions. First of all, you will need to weigh your rocket to determine its weight. Since this is the weight as it sits on the launch pad, you will want to include the weight of the motor. If you are using this calculation to help you pick which motor you're going to buy, you will most likely not have a motor available to weigh, but motor weights can be found on the internet. So weigh your rocket as it will sit on the pad and add the weight of the motor. This total weight will be what we use in our calculations. Now, if your mass is not already in kilograms, convert it to kilograms. We'll use a mass of 3 kilograms for our example. We will use a J300 as our potential motor. As you will learn in an upcoming video, the 300 following the J in the motor designation is the motor's average thrust measured in newtons. We will use this value but label it as force for our calculations. The mass of our motor is 607 grams, taken from thrustcurve.org, making our total weight 3.607 kilograms. Using Newton's second law, we can calculate the acceleration of the rocket from the force and mass, or force equals mass times acceleration. Rearranging the acceleration value is equal to force divided by mass, so we have 300 newtons divided by 3.607 kilograms for an acceleration of 83.17 meters per second squared. The acceleration gets us one step closer to our exit rail velocity, but we still need to calculate the amount of time between the ignition of the rocket motor and when the rocket leaves the rail. To calculate the time, we can use this equation. D equals initial velocity multiplied by time plus 1/2 of the acceleration multiplied by time squared, where D is the effective length of the launch rail. The effective length is the length of the launch rail minus the distance between the 2 rail buttons on the rocket. Using a 10-foot launch rail with a rail button distance of 2 feet, we have an effective length of 8 feet or 2.44 meters. VI is the initial velocity, which is 0 in this case, since the rocket started at rest. Since initial velocity is 0, time cancels out, leaving the equation D equals 1/2 of the acceleration multiplied by time squared. Rearranging this gives us time squared equals 2D divided by acceleration. Simplified, this becomes time equals the square root of 2D divided by acceleration. Filling in our values, we have time equals the square root of 2 multiplied by 2.44 meters divided by 83.17 meters per second, giving us a time value of 0.24 seconds. We now have all of the information we need to calculate the exit rail velocity with this equation. Acceleration equals final velocity minus initial velocity divided by time. Initial velocity is still 0 since the rocket began at rest, and we can rearrange the equation to become final velocity equals acceleration multiplied by time. Final velocity equals 83.17 meters per second multiplied by 0.24 seconds, giving 19.96 meters per second. Finally, we need to convert this value from meters per second to feet per second to see if it meets our minimum requirement of 50 feet per second. To convert our final velocity of 19.6 meters per second, we'll multiply times the conversion factor of 1 mile for every 1,609 meters times 5,280 feet for every mile. This gives us 65.5 feet per second, which is well above our minimum exit rail velocity. The J300 motor should provide enough thrust to get our rocket to a safe velocity before it leaves the launch rail. Another concern when selecting your rocket motor is the thrust to weight ratio. The hobby standard is to launch only rockets with at least a 5-to-1 ratio, meaning that the thrust is at least 5 times the weight of the rocket. This is pretty easy to calculate with the info we already know. 1 kilogram is equal to 9.8 newtons. 3.607 kilograms equals 35.35 newtons. The thrust, 300 newtons, divided by the weight, 35.35 newtons, gives us a value of 8.48. This means that we have a thrust to weight ratio of 8.48 to 1, which is well above the safe minimum value of 5 to 1. It is always a good idea to verify that your rocket motor will be a good match to your rocket before attempting to fly it. With these two calculations, you should be able to make that determination before purchasing your motor. Good luck in all of your rocketry endeavors, and thank you for watching the NASA High Power Rocketry video series.